I welcome you all to another video tutorial session on finite element procedure for solving structural engineering problem. In my last video, we looked at a symmetric truss problem with symmetric loading, and I gave an explanation, a theoretical background about symmetric truss analysis, and we analyzed a symmetric truss on the Ansys program. In this video session, we are going to analyze the same symmetric truss, but the loading on this truss is not symmetric, it is anti-symmetric. What is the meaning of anti-symmetric? If you check the full truss model on your screen, let me zoom in, we see the load defined in this manner. If we draw a line of symmetry about these two nodes, we see what is on the left hand side, what is on the right hand side. So immediately we know that our truss system is symmetric by shape, by geometry. But the loading, when we say loading is anti-symmetric, actually mean the loading on the truss actually tends to twist the truss. This is actually what I mean. Let's say the truss in its undeformed state. This truss is, there's a point here in its undeformed state without any load. There's a point here, and there's also a similar point here. When the truss is loaded, this point moves vertically upward by an amount, and also this point moves vertically downward by an amount, equal amount. If this point moves upward by an amount, say 10 mm, and this point moves equally downward by an amount, say 10 mm, without any movement in the x direction, we say the truss is under anti-symmetric load. So this type of loading tends to actually twist the truss system. For example, we have 2 kilonewton force here, and we also have another 2 kilonewton force here. Now see, the 2 kilonewton force are acting in opposite direction. It tends to twist the truss system about this line of symmetry, like a twisting force tending to counteracting each other. This force this 2 kilonewton force on the right hand side, we tend to move this portion, this half truss upward, and this 2 kilonewton force we tend to move this portion downward. There can be other type of load, but it can be, let's say we have an element here like this. Let's say we have more elements here. Sorry. Say we have 4 more elements to the truss. So they can be, if we have a downward load here defined at this node, we'll have an upward. For the loading to be anti-symmetric, we have to have an equal upward load at this point. So say here is 5 kilonewton downward, here will also be 5 kilonewton upward. So the anti-symmetric loading tends to actually twist the truss system about its line of symmetry. So that is how we identify anti-symmetric loading. And let me erase all this. And to try actually identify anti-symmetric loading, we'll notice that in this example, our horizontal loads are pointing in one direction. The horizontal load must point, see that there is no horizontal load on the truss, or the horizontal loads actually point in one direction, and the vertical load on the truss must be equal and opposite in both sides of the of the line of symmetry. For example, we have 2 kilonewton. We have 2 kilonewton upward force here, and we have 2 kilonewton downward force here. So the vertical load must be equal and opposite. So this is an example of an antisymmetric loading on a truss system. So when we have an antisymmetric loading case, we can analyze half model. Sorry. Okay. We can analyze. So for this example, instead of analyzing the full truss, we can just consider half portion of the truss. That is this point here. So that is what I have below. I'm considering just half portion of the truss. And because we have a line of symmetry about this point, and also there is a member along that line of symmetry, that means we need to reduce the cross-sectional area of that truss member by half in the half model. Oh, this is a mistake. So if the cross-sectional area of this element here, this one, if the cross-sectional area is A, the cross-sectional area in the half model will be A divided by 2. This is a mistake. A divided by 2. We have to reduce the area by 2. And because we have load acting at the node where the line of symmetry is passing, we need to reduce the value of that load by 2. Like in a full model, we have 2 nodes passing through the line of symmetry, this node and this node. And at this node, we have 2.5 kilonewton load. We also have 2.5 kilonewton load. We need to reduce this load by 2 because we are only considering half portion of the truss. So that is why in the half model it is defined as 1.2 kilonewton and 1.25 kilonewton and 1.25 kilonewton at both nodes. So this is the model for the half truss, and because it is symmetric loading, we need to apply roller support at a vertical roller support. So we need to apply vertical roller support at the nodes passing through the line of symmetry. So this is a vertical roller support here. So this is another vertical roller support. In the symmetric loading type, you will remember in my last video, we added horizontal roller support at the node. But for anti-symmetric load, we need to apply vertical roller support at the node passing through the line of symmetry. So that is just the brief explanation on anti-symmetric loading. And now we're going to go to the Ansys work environment. We're going to move to the Ansys work environment to actually analyze that problem. I'm not going to start from the beginning for this problem because in my previous video we already defined the geometry and the engineering data and the engineering material. So what I'm going to do, this is the static structural solver I used in my last video to explain symmetric loading. So I'm still going to use this same solver to analyze my anti-symmetric loading truss system because the geometry is the same. So let's call this a symmetric loading example. Say symmetry. Let's just call it symmetry. We need to duplicate this. So I click on it. I click on this arrow here and click on duplicate. So the static structure solver duplicates. So the static structure solver has created another copy for us. We have duplicated it. I duplicated this symmetric static structure solver rather. So this, you can name it anti-symmetric model. So you can see the engineering data and geometry is checked. Also the model is checked. We actually just need to run. But we're going to, the only thing we need to do in this exercise is actually to change the loading on the source system, because the geometry is exactly the same with the geometry of the symmetric loading exercise in my last video. So I double click on the model workflow to open the mechanical work environment, the mechanical interface. You can see, yes, it's right, starting mechanical. The mechanical work environment is now active, and as you can see, let me bring to focus. And as you can see, we have our food source, we have our food source section, we have our after section, we have two after section. So you see this also under the geometric branch, the section part. See this section part. So we don't need to change anything here. What we need to do, the support, we need to change the support. Under the static structure, we need to change the support definition and the force definition. For the food source, we have a pin support here and a pin support here. Let's see what we have in our Ansys model. We have a pin support at this point. There is string movement in the X and Y direction. We also have a pin support here. So this food source is okay. So let's check the first half thrust. Half thrust, we have a pin support at this point at the edge. We also have a pin support at the edge of the second half thrust. We have a horizontal we have an horizontal pin support, horizontal roller support at this node, but what we want to define is a vertical roller support. So you change the X component, you release it, and you restrain the Y component. That's just what you need to do. For this point, we also have a horizontal roller support there. We change it to a vertical roller support by restraining the Y component and releasing the X component. So for the second half thrust, we don't have any support at that node, but we apply symmetry. We apply symmetry region at this edge. So let's see, we'll get results using the symmetric using Ansys symmetric tool. So I apply a symmetric region at on this vertical element, noting this red object here is noting the symmetric tool which are attached to this vertical element that lies along the line of symmetry. So the supports are okay now. Let's check the force that are on the source. Let's go back to our PowerPoint. In our PowerPoint, at this node here, we have 2 kilonewton force pointing downward and 1 kilonewton force pointing to the right. So we need to define that on the Ansys program. I'm going back to mechanical. So this is the first, this first object on the structural tree is the first at this node here. So according to the S component, we say is 1 kilonewton pointing to the right. So you need to change it to positive 1000 here. The Y component is minus 2000 Newton, 2000 kilonewton force, 2 kilonewton force pointing downward. So you change it to minus 2000. This is the force acting at this node. This is the result of the two forces acting at that node. What again? At this node there, we have 2.5 kilonewton force. So let's define 2.5 kilonewton force there. Also, we also have 2.5 kilonewton force at this node. So we define those two loads now. So here we have horizontal load. The load is not vertical. So the Y component is 0. The S component is minus 2000, no, plus 2500. So the same thing for this load 4, 2500, 0 here. S component is 2500. So at the last node, what is going on? At this node, we have 2 kilonewton force pointing upward and 1 kilonewton force pointing to the right. So let's define that load. 2 kilonewton force. That is not the force, this is not the force, this is not the force. Okay, this is the force 2 is the force acting on that node. So we have what is it again? Sorry. 2 kilonewton force acting upward, 2000 Newton acting upward, and 1000 kilonewton pointing to the right, the x direction, and 2000 kilonewton pointing upward. This is what we have. That is the result of the force at that node. We do the same thing for at this force 5 is supposed to be 2500 Newton in the horizontal direction. The Y component is 0. The same thing for force 6, 2500 in the horizontal direction. No, it should be half of the load. Sorry. Now, because it's half Truss, so it should be half of this. 2500 divided by 2. This is 1250. For 6 will be 1250. The Y component 0. The component here, we have 2000 kilonewton pointing upward, 1000 kilonewton pointing to the right, 2000 kilonewton pointing upward. That's what we have there. At this point, we have 1000 kilonewton pointing to the right, 2000 kilonewton pointing upward. Here we have 125 Newton pointing to the right, 0 in the Y direction. Same thing here. We have 1250 Newton to the right, the Y direction 0. So this is the load definition. I've edited the load definition on the truss, the full truss and the half truss. So now can see the results that are available that can be displayed. Directional deformation in the x direction. This directional deformation is for deformation in the x direction. You can see the orientation here is set to x axis. The second directional deformation is for deformation in the y direction. We have axial force. We need to rerun this analysis. These results are actually not correct. This axial force. This will display our axial force in the member, force reaction. This will display the force reaction at this node. This will display the force reaction at this node. This will display the force reaction at this node, and this will display the force reaction at this node. So we can run analysis now. Let's run so take some time. So now the result has run. Can now visualize our results. Let's check the deformation mode. You can see how the truss is moving. But my second half model is not deforming. I actually applied the Ansys symmetric tool on this second half truss model. It seems that for anti-symmetric loading, the Ansys symmetric tool does not work for anti-symmetric loading. It only works for symmetric loading. So you should take note of this. So when we have a symmetric load case, we need to define our support manually, as I've done in this video, by applying vertical roller support at the node passing through the line of symmetry. You can see the truss is deforming a similar pattern. This is the full truss element, and this is the half truss element. You can see on the right hand side, this element here is in compression. This element here is in tension. We shall see that the axial force in this element, the axial force in the right element is, we also have the same axial force in the left element, but the direction of the force is different, is opposite. Let's probe the axial force for our full model analysis and our half truss analysis. So I'll click on the axial force, click on this probe button here. So we see that the value here is 1,346 Newton. Also have the same thing in the half model analysis. Also here we have 1,274.8 Newton. We should also have the same thing here. Here we have 0. We don't have any force in this member. We should also have 0 here. We should also have 0 there. Let's check the force, the value of the force here. I see this is 1,246.3 Newton. I think this will be in Ansys positive axial force means tension, while negative means compression. So you can see that the value of these two mirror elements are the same, but they have different direction. This is in compression, 1,346.3 Newton compression member and tension member, while on the right hand side we have 1,346.3 Newton compression member. The same thing here, we see that the forces are equal but opposite. We have 1,274.8 Newton, we also have minus 1,274.8 Newton on the right hand side. So this is actually the characteristics of an anti-symmetric loading. I actually did not explain this in my PowerPoint. I wanted to explain it. The axial force at the axial force of the mirror elements are equal but opposite. If we have a tension member in one side, we'll have a compression member in the other side. So that is one property of symmetric loading. And also, if we check the deformation result, you can get the deformation. Here, this joint is free to move. So this is the deformation at this joint, very small value. So this also is deformation at this joint. At this support is 0 because we have supports defined at those points. I, oh, this is actually giving us a value. I'm surprised. It's not supposed to give us a value because we have a support at that point, but it's a very, very small value. So it's finite element procedure. Sometimes we get marginal error. The same thing here. We have a very, we're supposed to have, we're supposed to get 0 deformation at this point, but we are getting 2.8819 times 10 minus 4. A very, very small value in millimeter. Because it's finite elements, sometimes we get marginal error in our analysis. So you should be able to detect this error, and you should know that it's not cause for alarm. Let's check the deformation at this point. Actually the same. Also at this point, you can see the results are the same. These are the deformation in the x direction for the deformation in the full model and the half model in the x direction are exactly identical. In the y direction, don't think there's deformation in the y direction. All the components are blue. I see 0, 0, 0, 0. So there is no deformation in the y direction. Don't have deformation in the y direction. So there is no deformation in the y direction at the node point, even about the source element. The force reaction, let's look at this force reaction. We can compare with this. Force reaction, we check the tabular data, the x value, the x reaction is minus 3,500 Newton. The y component is minus 1,250 Newton. We should check force 3, it's also the same thing. S and the y component are the same. So this is how we consider antisymmetric loading to reduce our model by half using the finite element procedure. So I've come to the end of this video session now. In my next video session, we are going to treat 3D truss analysis, 3D truss system. 3D truss system has many applications in real life. You can see the application in a tower crane, which is used in construction. The tower crane structure is a 3D truss system. Also, escalator, which you find in building for moving from one floor to another. The structural frame is made up of truss system. We have bridges that are truss type. So we can also apply finite element procedure for solving 3D truss problem. So in my next video session, we're going to look at 3D truss system using finite element procedure both on MATLAB and also on the Ansys program. Thank you so much for watching my video. I hope you have learned one or two things from this video, and see you next time.